Okay. So today we do the inverse of a matrix. And before we do that, we're going to be dealing with these. Anyways, this just ties together the systems of equations we did in chapter 7 with what we're doing now. And we're going to get back to this, right, in the next lesson. But, you take a system of equations here and you write a matrix. An augmented matrix would be where you take the coefficients 1, -4, 3, right? 1, -4, 3. And then the 5 goes on the other side, right? -1, 3, -1. 2, and because there's no y, it's a 0, and a -4, and 6. So we really, when we see these kinds of matrices, and really what we're looking at are systems of equations. But that's why we do it, right? That's the whole reason we're doing matrices, is because we're going to use them to represent systems of equations. Okay. So let's do one, right? Let's write our augmented matrix out of this, just as a little bit of practice. I know it's pretty easy stuff. What's going to be the first row of the augmented matrix here? 1, 1, 1, 2. 1, 1, 1. And, they had a dotted line in between the ones on the left and the column on the right, but it doesn't matter. What about the next row? 2, -1. 2, -1, 3, -1. And the last row? -1, 2, -1, 4. So we're kind of appending a matrix to a matrix. That's the augmented matrix. There's a couple things to just, before we can really do because it's such a, I'm kind of like piecing together things from different chapters. Sometimes I got to reach back and define a thing, So we are going to be doing a little bit of this today. Another thing that we've got to do that was in the end of section 8.2, but we didn't talk about it because we didn't use it yet. But there's such a thing called an identity matrix. An identity matrix is a matrix which is square, first of all. What do you think it means to be square? Same number of rows and columns, right? And it has ones down the diagonal and zeros everywhere else. That's what an identity matrix is. So for example, let me do this because I don't think I left enough space for this. If I multiply a 3 by 3 identity matrix times, it doesn't matter what the matrix is, maybe just to make the point, I'm going to make it 1, 2, 3, 4, 5, 6, 7, 8, 9. And see how that works, right? To do the first row, first column, I would take the first row and the first column, multiply and add, right? So the first, I'm going to get 1 times 1 plus 0 times 4 plus 0 times 7, which is 1, right? Then I'm going to get, for the next, 1 times 2 plus, what am I at? First row, second column. 1 times 2 plus 0 times 5 plus 0 times 8. What I got going wrong here? It seems like I'm doing something wrong. Oh, no. So to find the first row, second column, I use the first row, second column. Why is that not working? See, we did this one and we got it correct, right? And now we should be using, yeah, but it ought to zero out on everything, right? No, I'm sorry. I'm thinking something wrong. Okay, now we get 2 plus 0 is 2. I was thinking something else. 3 plus 0 is 3. So you can see how it's picking out just these values. 0 plus 4 plus 0. 0 plus 5 plus 0. 0 plus 6 plus 0. Right? And we could finish that up. 7, 8, 9. So when you have that kind of a matrix, then any matrix you multiply by that you'll get the same thing back again. Right? So we can call this is the I matrix. Right? I for identity. And I times anything is that same matrix back again. So the definition is here. Okay? So it has to be square, same number of rows and columns. And they're saying you can denote it by I sub n or just use I. Capital I means identity matrix. Okay. Once we have the concept of identity matrix, then we can go to get at this. I mean, last time we solved matrix equations by doing addition, subtraction, scalar multiplication, right? That was all we really had in our toolbox to do that. Now we need something else. This is a real number algebra equation. If I had to solve it for x, what would I do? It would divide by a, right? But remember what we said last time. There is no such thing as matrix division. I can't do this, right? X equals b over a. Does not work. Right? That does not work. So the way we have to solve it is we need to come up with this concept of an inverse matrix, right? And then we're going to multiply both sides by this inverse matrix. Right? And when you multiply an inverse matrix times the matrix itself, you get I. So if we can come up with this inverse matrix that when you multiply times the A gets you I, then we would have I times X equals A to the minus 1B. And what would I times X equal? Because it's the identity matrix, it's just going to be the X, right? So our solution for solving an equation which is like that is we need this thing, an identity matrix an inverse matrix, such that when we multiply it times the A, that it gives us the I matrix. Okay, so that's what the lesson is today. How do we come up with this matrix A to the minus 1 that'll help us solve an equation like that? Okay. So two matrices are inverses if, when you multiply them together in both orders, A times B, B times A, you get the identity matrix. There is a line in the textbook that says, you know, if you're verifying the two matrices are inverses, you multiply A times B and you get I. There's really no reason to do the second check. All they say is it can be shown that if it passed this check, it will necessarily pass this check. So really, it is sufficient to just do one of these. Just in either order, multiply the two matrices, and you ought to get I. It wouldn't matter which order. Okay. So to show the two matrices are inverses, you got to multiply them together and see if you get an identity matrix. And you know how to put this in the calculator. I'm going to do it longhand. Just we could make this whole lesson 5 minutes. A times B, right? 2, negative 1, negative 3, 1 times negative 1, negative 1, negative 3, negative 2. Okay, so first row, first column, 2 times -1 plus -1 times -3. So that's -2 plus 3, 1. Okay, first row, second column, 2 times -1 plus -1 times -2. That's -2 plus 2, 0. Right? Second row, first column, -3 times -1 plus 1 times -3. That's 3 minus 3, 0. And last, -3 times -1 plus 1 times -2. 3 minus 2, 1. So we just showed that those are inverses because when we multiplied them, we got an identity matrix. Right? That's the identity matrix for a 2 by 2. Right? Ones along the diagonal, zeros everywhere else. Yeah. Yes. It's got to be top left to bottom right. Okay. So how do you find the inverse matrix? I mean, it's one thing to say, here's two matrices, show their inverses. It's another thing to actually find the inverse matrix. Okay. And we're going to see what we do is we augment the matrix that we want to find the inverse of. Let's say we want to find the inverse of A. We augment A, which has got to be a square, with an identity matrix of the same dimensions. Right? And then we do what's called row operations to take it from A augmented with I on the right of it, so that I is the matrix which is on the left, and whatever is left on the right-hand side, that's going to be our inverse. It's hard to explain, but when you see it, we'll see what we mean by that. So by row operations, we haven't done this yet. Again, if we would have done things in a different order, we might have seen some of this, but this is just as good a time to figure it out now. Right? Row operations were defined back in section 7.3, which we didn't do. Right? We did the first part of solving with substitution and elimination, and that was great for 2 equations and 2 variables. When you got higher than that, they did some things where they were using row operations to solve. So you could see row operations in a system of equations means, you could like switch the equations where they're written. That's fine, doesn't change the system. You can multiply one of the equations by a constant. That wouldn't change anything. Or you could add equations together and replace one of the equations with that result. And we have basically the same thing that we can do with matrices that we can do up here. And that's what we mean by the row operations that are going to find our inverse for us. So this is what we mean by we are going to try to find the inverse to this 3 by 3 matrix. Right? So first what we do is we augment that 3 by 3 matrix with an identity matrix on the right. Right? So since that was 3 by 3, here's our 3 by 3 matrix. It's got ones down the diagonal. It's got zeros everywhere else. Now, what we're going to try to do now is in some way combine, just like we would eliminate variables by adding the equations together, we're going to try to eliminate some of these numbers so that we make this left-hand side be the identity matrix. We would like to create zeros by combining rows, create the zeros here, 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 and here. And there should be ones down there. If we can use row operations to make an identity matrix here, then whatever is left here, that's the inverse. Okay. So I'm showing their example, and I'm just showing it like in pieces, right? Here's the matrix we're trying to find the inverse of. Here's our first augmented matrix. We've just written an identity matrix next to it, nothing else. Okay, this is the same as the last line on the last slide is this. Now, in order to make a zero in this position right here, right, you can see what they said. They took the first row and the second row up here, and they added them together, and they put the result here. So add up 1 plus 1 is, sorry, actually they did negative R1 plus R2. So it'd be negative 1 plus 1 is 0. It's kind of like when we multiplied to find equivalent systems with systems of equations, right? So here we're doing negative this row plus this row and put the result in this row. So we did this one, negative 1 plus 1, we got that. Next we're going to do negative 1 times negative 1 is 1, plus 0 is 1. Right. Negative 1 times 0 plus negative 1, negative 1. Right. Negative 1 times 1 plus 0, negative 1. Negative 1 times 0 plus 1 is 1, and negative 1 times 0 plus 0 is 0. Right? So the whole point of that is we are trying to create a 0 in this spot because we need this to be the identity matrix here. Right? We need 1s along here, 0s everywhere else. Okay, now in order to make a 0 in this position, right, in this position, it looks like we're going to do negative 6 times R1 plus R3, because, you know, what will that do? You could see right away, that'll be negative 6 plus 6, there's your 0. Right? So negative 6 plus 6 is 0, but now you got to do the same thing for every other column. Negative 6 times negative 1 is 6, plus negative 2 is 4. Right? And just, you can follow it along. Negative 6 times 0 plus negative 3, negative 6 times 1 plus 0, negative 6 times that plus 0, negative 6 times 0 plus 1. Right? So we created these zeros. Okay, where else do we need to create a 0? We need zeros here, 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 and here. So next slide. Right. This was the one we just did. Now we're going to use this to try to create these two zeros. Right? Try and make this and this. And now, you know, when you do row operations, different people might solve it in different ways. I mean, you may do a different combination of rows to make your zeros. So this is what they did on theirs. So this, starting with this one, yeah. Most of the time, you would probably do it separately. But I'm just showing their example. They're doing more than one in one step. But in any case, if I wanted 0 here, I mean, you should see, well, you know, if I added these two rows, that would do it. So let's do that. So they're just adding R2 and R1. This row, that's R1, and that's R2. Add them up. And where am I at? Here. R2 plus R. Okay, we're in this row here. So we're adding up these two, and we're putting the result here. Okay, so 1 plus 0, negative 1 plus 1, 0 plus negative 1, 1 plus negative 1, 0 plus 1, I should be pointing with this, and 0 plus 0. Right, that's this row. And then in order to make a 0 here, right, we're going to do negative 4 times this row plus this row. Then these will cancel. I mean, you see what you got to do now is you got to be careful. I don't want to create a 0 here and at the same time fill in the 0 that I already made on the first step, right? So I don't want to combine this row with this row because I would end up introducing a number again. So we're definitely doing something in between these two rows. So negative 4 times this row plus this row, I keep my 0 here. Negative 4 times that plus that is 0. And then you can follow their math all the way down. That's where they're getting this new row. Okay, now which other zeros do we need to make so that we have the identity matrix here? These two right there, right? So the last slide. Right, now we're taking, this was the result of our last step. We're going to use those to combine and make that. So let's see. I want to add these two up in a way that does not create a 0 where I don't want one. So let's see. They're saying let's do R3 plus R1. Right? If I add R3 plus R1 and I put the result here, right, I'm going to get the 1 there, 0 there. Now I get 1 plus negative 1 is 0. Right? On this side, negative 2 plus 0, negative 3, negative 4 plus 1, 1 plus 0. And the same thing, now they're adding 2 and 3. right? Because when they add 2 and 3 and put the result here, it'll cancel -1 plus 1, and you get the 0. So by doing all that, right, we just created the identity matrix in the first 3 columns. What's left on the right-hand side, that's the inverse of the matrix we started with. Again, you can show that by multiplying, right? -2 plus 3 plus 0, 1. -3 plus 4 plus, what is this? I think I moved. That should be a 0, right? Because that's where I'm getting a little goofy. -3 plus 3 plus 0, 0. Okay, 1 minus 1 plus 0. Okay, -2 plus 0 plus 2. -3 plus 0 plus 4, 1. Okay. And 1 plus 0 minus 1. Last one. -12 plus 6, which is -6, plus 6, 0. -18 plus 6, which is -12, plus 12. And the last, 6 minus 2 minus 3, 1. So that's row operations to find the inverse of a matrix, and we verified that is the inverse of a matrix. Okay, let's see if we can come up with our own here. Yeah. Yes, they could. He's saying, can you find matrices that don't have inverses? Yeah, that would be like finding a system of equations that doesn't have a solution. So do we sometimes have systems of equations that don't have solutions? Yeah, we do. Okay, let's see if we can do this one without too much gnashing of teeth. Okay, 1, -2, -1, 0, -1, 2, 1, -2, 0. All right, and then we'll put the what's that? It doesn't matter. I mean, if you want to put some dots in there. So let's see. How do you think we could make a 0 here? We need to make a 0 in this position. We already got one there. What combination of rows could I do that's going to, how about, multiply this one by -1 and then add it to this one, and that would work. Okay, so let's do that. I have a feeling this is going to not work because you can see we're just going to fill up too many slides, and somehow you got to capture what we just did. So let's see, this one stays unchanged. 1, -2, -1, 1, 0, 0. This one stays unchanged. -1, 2, 0, 1, 0. And now we're going to basically take row 3 minus row 1. 0, 0, that's good. 1, -1, 0, and 1. Now, let's see if it'll let me do this. Probably not. That's okay. Edit, copy. Oh, I was already there. Edit, paste. Yeah, not bad. So let's erase this stuff up here. And then grab all this stuff and move it up. Okay, now we've got to make a 0 here. How do you suggest we can make a 0 there? I mean, you only got one other number to add against, right? So I could say, how about we multiply the middle row by 2 and add it to the first row and put the result there. Right? So this will be a times 2 in this row right there. Actually, negative 2. Right? So this will be, let me try and get more than one on here. So negative 2 times that plus that is 1. Negative 2 times that plus that is 0. Negative 2 times that is negative 4 plus negative 1 is negative 5. Negative 2 plus that, 1, negative 2, and 0. Right. Now everything else is unchanged. 0, negative 1, 2, 0, 1, 0. And 0, 0, 1, negative 1, 0, 1. Okay, let's try to do the next one right here.
Wait, can you explain like how you got that? Like, can you read? Never mind. I know.
I mean, how did we get from here to here?
Yes, like for the top row.
For the top row.
Like what is?
Right now, we multiplied this row by negative 2, and we added it to this row.
Okay.
1 times this row plus negative 2 times this row, and we put the result there.
Okay.
Right? And so we put the result right there. Okay, now we need to make another 0 where? Yeah, I mean, somehow we need to combine these two and put the result there to try to get rid of that negative 5, make it a 0. So what do you think we would do? How about we need 5 there, right? How about we'll multiply this one by 5 and add it to this one and put the result there. Right? So make 5 times this row plus this row and put the result there. Okay, so that'll be 1, 0, 0, okay, and then 5, negative 5 plus 1, negative 4, right? Negative 2, negative 5 times 1 is 5. There we go. And nothing else changes at this time. So we have 0, negative 1, 2, 0, 1, 0. 0, 0, 1, negative 1, 0, 1. Wonder if it'll let me just keep scrolling down. Yeah. Okay, now we need one more 0. Yes, we got to, well, we'll deal with that later, okay? First, let's make our 0 in this spot. What combination of, yeah, what if we do this one by negative 2, and we add it to this one, and we put the result here, okay? And that'll give us this. This one, the top row stays unchanged, 0, 0, negative 4, negative 2, 5. And now we're going to, for the second row, these will give us a 0, 0 plus negative 1, negative 2 plus 2 is 0, positive 2 plus 0, 0 plus 1, negative 2 plus 0, and the last row stays unchanged, 0, 0, 1, negative 1, 0, 1. Now, do we have the identity matrix on the left? What's wrong with it? Remember, we had one of the row operations you could do is just multiply by a constant, a non-zero constant. So let's just multiply the second row by negative 1, right? Multiply this one by negative 1. And now we have our final solution, right? 1, 0, 0, negative 4, negative 2, 5, 0, 1, 0, negative 2, negative 1, positive 2, and 0, 0, 1, negative 1, 0, 1. Okay, so that would make this is the a minus 1. So instead of doing it by hand, let's remember how we put that in the calculator. Right? We need to define, we need to put in the calculator first that matrix, right? Define our A by putting that in. Remember, where do you go in the calculator for a matrix? It's above the x to the minus 1. Second, x to the minus 1, edit. Okay. Remember, what are they asking for at the top of the screen? What do they call that again? The order, right? So these are 3 by 3 matrices. So put in your 3 by 3. Okay, and now we'll do 1, negative 2, negative 1, 0, negative 1, 2. Oh, I messed that up. That was a negative 1. Got that right? 1, negative 2, 0. Okay, so we get that in there. Now we need to do the B matrix, right? So that will be, scroll down. Can I scroll down? Yeah. Right. That's the A to the minus 1. We'll put it under B, right? So let's go. Matrix, edit, 2, and now we need a 3 by 3. Negative 4, negative 2, 5, and negative 2, negative 1, 2, and negative 1, 0, 1. Okay, now how can I show those are inverses? Multiply them, right? Go back to this screen and go second matrix 1, second matrix 2. And if you get the identity matrix, you just found the inverse. We got the identity matrix. Now, let me see what's next. Okay. Now, the next thing that we do here is we actually learn there's special procedures that we're supposed to know for a 2 by 2 matrix only, which are simple and are not easily done on a 3 by 3. And the truth is, nobody does row operations to do this stuff, right? What they do is they put it in their calculator, right? Like we already did, right? If you want to know what the inverse matrix of our A is, what did I just do? I just went way too far down, right? Come on. I don't know why it's doing that. Okay. Doesn't like it. It doesn't matter. Just understand that instead of having to go through the row operations, if you put that matrix on matrix A like we did, then on this screen, you just go second matrix 1, and then you hit the x to the minus 1 button, the same button where the matrix is, right? So just hit x to the minus 1. So you want to know the inverse? There it is. I mean, we know that, row operations would probably be too complicated. But when they talk about solving equations by one of the methods they said was Gaussian elimination, means that's Gaussian elimination. It's actually a variety of Gaussian elimination. That's what we used to have to do to find these things. Okay. Right. The special procedures for a 2 by 2 matrix are like this. Right? If you got a 2 by 2 matrix, and we'll just call each entry A, B, C, D, right? Then in the matrix, you switch the position of the A and the D. Okay. No, that's right. Thank you. You switch the position of these two, and then you put minus signs in front of the other two. And then you divide by 1, or you multiply by 1 divided by AD minus BC, right? So for example, in this particular problem here, right, probably the easy thing to do is first, let's do the AD minus BC for this one on the left, okay? Then we'll get AD minus BC, okay? Remember how we labeled these, A, B, C, D. So that'll be 3 times 2 minus negative 2 times negative 1, right, which is 6 minus 2, which is 4. So the inverse, a to the minus 1, is 1 divided by 4 times, and now we just take this matrix, remember, switch the A and the D, 2 and 3, and then make these two the opposite of what they are. Right now it's negative 1 and negative 2, so make it positive 1 and positive 2. And again, what kind of operation is it when you multiply a matrix by a constant? What did we call it? Scalar multiplication, right? So then you do the scalar multiplication, right? Which is 2 over 4 is 1/2. 1 over 4, 2 over 4, 1/2, and 3 over 4, 3/4. And again, you can verify that in your calculator. Let's go second. Well, the easy thing to do is let's just define matrix A, right? We'll go over edit 1. This one's a 2 by 2. And we're going to put in 3, negative 1, negative 2, 2. And then go to the main screen and just go second matrix 1, a to the minus 1, x to the minus 1. 0.5, 0.25, 0.5, 0.75. I wonder. Let me see if I do math, enter, whether it turns it all to fractions. Math, enter. Yeah, and then it turns all to fractions. Right. They don't say it in this part of the chapter, right? But this thing, when you do the AD minus BC, is called the determinant of a matrix. Kind of, I mean, we use the same word in the quadratic formula. The b squared minus 4ac is the determinant. Same name, determinant. Okay. Now, if we do the next one, right, see what happens. First step, let's calculate the AD minus BC, the determinant. AD minus BC. 3 times 2 minus negative 6 times negative 1. 6 minus 6 is 0. So what's going to happen when I do scalar multiplication with 1 divided by 0? It's undefined, right? It's undefined. You can't divide by 0. So when that's what it is when it says if possible. This is when it's not possible. This is when you don't get an inverse, right? Not possible. So we don't have the same kind of procedures for 3 by 3s. I mean, I think there are those kinds of procedures, but even the thing of calculating the determinant is so much more complicated with a 3 by 3. I mean, I think the calculator will do it for you. If you go in the calculator and look at matrix menu, right? We've used the names and we use the edit, but what happens if you scroll over to the middle column, right? That first one is the determinant. That's the AD minus BC, and it does it for you. And if you have a higher, if you have a higher order square matrix, it'll do that too. There are procedures for doing that. We just don't do them. Okay. And that is the end. We know what augmented matrix are. We can verify matrices or inverses of each other, the row operations, and using that formula to do the 2 by 2, inverse of a 2 by 2. Right? You can do any of these any way you want, right? I mean, I would recommend, I think it's in here, that there's like a chance to do like a row operation for a 2 by 2 and a 3 by 3. I'm not gonna have a test question, which is a row operation, because that would be like impossible to grade. Just a minute.